This is Calc AB, and this is section 2.5, implicit differentiation. Remember, we want to test 2.5 and 2.6 on Friday. And that would be the 14th, the last day of the quarter. So what I want to do is start 2.5 on this video. You can look at this at home. You should look at this at home. And then when we come into class on Monday, you'll be able to do most of the problems out of the problem set. And then I'll try to wrap up any questions you may have on Monday about implicit differentiation. And then we can start 2.6 on Tuesday. And I'll probably do another short little video so you can look at it at home and come to class pretty much prepared. Okay, so let's see, 2.5 implicit differentiation. There's a little discussion here about explicit functions where you have y as a function of x, y is a function of x. In this case, it's parabola, 3x squared minus 5. However, there's some equations where you do not have y equals. For example, this one, you have x is equal to, or xy is equal to 1, which can be rearranged explicitly, right? So this is said to be explicit, and this is implicit. And you can look at the little notes there on this page. You should probably read this page reasonably well. Okay, now later in the page, they give an example. So what I want to do is I want to go through these examples. Now, obviously, you have it printed out in the text, but if I do it up on the board at the same time with my voice running, either I'll put you to sleep or sort of reinforce what the author is saying. The first example, this is the derivative with respect to x of the function x cubed, and we can just use our power rule here. Pretty straightforward. 3x squared is the answer, done. The note that you should be seeing here is that the variable in the function is the same variable of which we're taking the derivative with respect to. Sounds a little bit wordy, but that's going to be the case. Well, that has been the case in all the functions we've seen so far. Second one, we're now taking the derivative, again, with respect to x, but we don't have an x function here. We have y cubed. So we sort of have to think, well, y might be some complicated function of x. Y is a function of x. And the way that you're going to differentiate this is you use the power rule. That's going to be 3y squared. But then you have to follow it by the derivative of this guy. Okay, so we're going to follow it by the derivative of y with respect to x. And a lot of students get a little bit confused about that. And why didn't you do it up here? And the answer is we really did do it up here, right? We followed this using the chain rule with the derivative of x with respect to x. Well, you can sort of suspect the derivative of x with respect to x is just 1, so you don't have to put it there. Here we don't know what y is. The derivative of y with respect to x is dy dx. So that was example 1b. Let's look at 1c just for a minute. And what we're going to do is we're going to see these start to combine implicit and explicit functions. So in C, we're taking the derivative with respect to x again of x plus 3y. Okay. Well, the derivative with respect to x is easy. That's just 1. And the derivative with respect to x of 3y is going to be 3. Now, it's not just going to be 3 times 1, but 3 times the derivative of y with respect to x. And again, I think the way to think about this is whenever you see a y in the thing that you're differentiating and you're taking the derivative of that, that has to appear over here. If you see an x in the problem and you're differentiating with respect to x, I suppose you could put it in, but it would just be dx dx, which you don't have to write, right, because that's 1. Okay, so for at this point anyway, we're going to see y's and x's. And if you ever see a y in the problem, you have to use the chain rule. Okay, the last example is a product. We're trying to find the derivative with respect to x of x times y squared. So we have to use the product rule. So as we go through this, let's see, the derivative of a product is the first times the derivative of the second. Now, the derivative of y squared, we start with the power rule. That's 2y to the first, okay? But again, note there's a y here, so we have to follow this by the derivative of y with respect to x. So we're in the middle of the product rule. The derivative of the product is the first, that's this, times the derivative of the second, plus the second, y squared, times the derivative of the first. And when you differentiate x with respect to x, you just get 1. Okay? Let's see. Turn the page. There's a few guidelines here. Differentiate both sides of an equation with respect to x. Any term that has a dy dx in it, you're going to move to the left side, move everything else to the right side. We actually saw these in pre-calculus, by the way. Factor out the dy dx and then solve. An example. We've got, let me just pull up you have it all written here, but let me just pull up a blank screen and we'll work this problem and sort of talk through it as we go. So for here, we have this complicated looking equation. It says y cubed plus y squared minus 5y minus x squared is equal to -4. The graph of this creature is shown on the lower left-hand side. It has some weird bucket-looking shape. You know, it comes zipping in. It looks like this. Obviously, y is not a function of x because this thing fails the vertical line test pretty miserably. Right? So as you move your vertical line, you can see it hits it in more than one spot. So not a function of x, but we say that x and y are related implicitly. Okay, so the task is now to find the slope of the tangent line. So again, let me just quickly throw this back up again. We have this strange looking graph, and there's a point on the graph that's actually given. It's the point 1, -3, right here. This is 1, -3. You might want us to test to see whether or not that really fits in here. If you were to put 3, -3 and cube it, and then -3 and square it, and then -5 times -3, and then -1 squared. Check to see whether or not that really does equal -4. I'll leave that to you. The claim is this point is on the graph, so this equation had better be true. Right? Otherwise, the point, if it doesn't satisfy the equation, it can't be on the graph. But the task now is to try to come up with the slope of this tangent line. So what's M10? M10. And slope of tangent lines are always rise over run, always dy dx every time. So our task out of this problem is to find dy dx. Okay? And we don't have this as an explicit function of x. Y and x's are all tangled up. So let's just start differentiating implicitly. The derivative of y cubed, 3y squared, times dy dx. Remember, again, you note the y here. Whenever you see a y, you're going to have a dy dx in your derivative. Not so much for that, right? Okay, next term. The derivative of y squared is 2y to the first. No, I don't have to write the 1 there, but just to emphasize, we're using the power rule, times dy dx. And the derivative of -5y is -5 dy dx. And the derivative of minus x squared is -2x. And the derivative of the constant is 0, right? The derivative of constants are always 0. Okay. Take away my smiley face. Oops. -2x equals 0. Okay, now the task is to solve for dy dx. So we look at this and we see there are 1, 2, 3, 4 terms on the left. And remember, terms are things that are added and subtracted. So all of these are the terms. There's one term on the right. What we're going to do is keep all the terms on the left that have dy dx, and anything that doesn't have dy dx we chuck over. So that becomes +2x. Now, of these remaining terms, notice that they all have a dy dx in them. That was sort of purposefully done, dy dx. So all we have to do is factor out that dy dx. Let's factor that out. Dy dx, and we have 3y squared plus 2y minus 5. Okay, and that's now equal to 2x. I suppose we can move all of this over here to make it look a little bit prettier. And now we're solving for dy dx. So just divide out, and you have dy dx is equal to 2x over 3y squared plus 2y minus 5. Now, if you wanted to evaluate this at a particular point, right, we would need to have both the x and the y coordinates. Well, they did give us that. They gave us the point that we were looking at was 1, negative 3. So we can go ahead and plug those numbers in and calculate dy dx at that point. So let's just go ahead and finish it that way. Dy dx evaluated at 1, negative 3 will be equal to 2 times 1, putting 1 in for x, 3 times negative 3 squared plus 2 times negative 3 minus 5. We clean that up. We have 2. So this is 27. Take away 6 is 21. Take away 5 is 16. Right? 21 take away 5, or 1/8. Okay, and if you look at the sketch, it sort of seems plausible. There's our weird curve again, looking like a basket of some sort. And at this point, the slope does seem to be a small positive number. 1/8 is the right answer. Okay, I want to skip example 3. Now let's go to example 4. Find the slope of the graph. So once again, we have a figure. The figure is given in the left-hand margin. I've reproduced it over here. It's an ellipse. And we have a point that's given on the ellipse that has these coordinates. For this one, we'll actually go ahead and double check and make sure that those coordinates satisfy the equation. But the task is to find the slope of this tangent line. And they've shown it graphically. Our task is what is the slope of the green line. Okay, so here's the equation. First of all, let's go ahead and just do the algebra. Verify that the point root 2 minus 1 over root 2 satisfies this equation. So root 2 squared, right, we're putting x right there, plus 4 times negative 1 over root 2 squared is supposed to be equal to 4. So let me put a question mark here. Our task is to make sure that it does equal 4. And if it does, then that point lies on the equation or on the graph. So what do we have? Root 2 squared is 2. Root 2 squared is 2. So this is 4 divided by 2. And does that equal 4? Yeah, it does. 2 plus 2 equals 4. Okay, so this is a good point. Now, let's see if we can find the slope of the tangent line. Okay, so they've got it worked out here. I'm just going to pull up a bare screen again and do it from first steps. Okay, x squared plus 4y squared is equal to 4. This is a geometry equation, right? Geometry equation, it describes the graph of this ellipse. Analytic geometry, I suppose, but yes, it is the equation. Okay, now we want to write a calculus equation. So this is geometry. Now we're going to do calculus. Calculus is going to be dealing with the rate of change, right? And the rate of change that we need is the derivative of y with respect to x, because that's going to give us our slope of the tangent line. Okay, so let's attack this black guy and get the rate of change. So we differentiate with respect to x. Okay, so 2x, right? The derivative of x squared is 2x. The derivative of 4y squared, we start with the power rule, right? Bring the power down, that's 8, y to the first. Right? Again, if you want to put a 1, you don't have to. 8y to the first. But because we're differentiating with respect to x now, and that's not an x, we have to include, using the chain rule, the derivative of y with respect to x. The derivative of 4 is 0. When you differentiate a constant, you always get 0. So let's solve this for dy dx. I would take the 2x and chuck it over. 8y dy dx is equal to negative 2x. And now we're going to go ahead and divide by 8y. So dy dx is equal to negative 2x divided by 8y, which cleans up a little bit, negative x over 4y. Okay? If we want to evaluate that at this particular point, we can go ahead and plug in the ordered pair, root 2, and then minus 1 over root 2, and calculate the slope of the tangent line. So let's see, we're plugging in for x, root 2. So this is negative root 2. And for y, we're plugging in minus 1 over root 2, so that's minus 4 over root 2. Nice little complex fraction here. So let's invert and multiply. We have negative root 2 over 1 multiplied by root 2 over negative 4. So root 2 by root 2 is 2, negative, right? And 1 times negative 4 is negative 4. The negatives cancel, and we get a half, which is sort of consistent by looking at the picture, right? Wherever the picture was here. The slope of this m tan is a half. It appears to be a half, 1 up and 2 over. Okay, so that's example 4. What else do I want to do? Example 5. This is on page 144. That's gross. We have something called a Lemenscape, right? It's a weird picture. It looks like a figure 8. No, you're not expected to be able to graph this thing, but the curve goes around. It looks like it's tangent to the x and y axis. And there's a point that's given, 3, 1, that supposedly satisfies this equation. And again, you might want to go ahead and double check, put in 3 and 1 in there, and just see whether or not you get a true statement. Okay, and again, the task is to find the slope of this tangent line. Okay, it looks to be about 1, because that looks to be about a 45-degree line. When you go through all of this, lottie-dottie-dottie, all the way at the end, you find out that the slope is in fact 13/9, so not 1, right? A little bit more than 1. 1 would be 9/9. This is 13/9. Okay, but I'll let you go ahead and play with that one. See if you can follow through. Notice at this stage, this is the calculus step, right? And that's the only thing that requires calculus, going from here to here. Everything after that is algebra. It's actually pre-calculus, just solving for dy dx. You might want to play with that one on your own, double check, and make sure you can get to this dy dx equals down here. Dy dx is equal to this thing. Right? Okay, and we can answer that or play with that on Monday if you like. Let me go ahead and stop the video here. You've got certainly some work to do. Okay, so that's 18 minutes. That's not long. Have fun differentiating. By the by, on this, you know, I did put in a bunch of the, wherever we are. I guess I didn't. Okay, so the problem set, right, starting on page 146, you can certainly do the odds. So start 1, 3, 5, 7, 9. Right? Same thing with 21, 23, 25, 27. There are some famous curves. The Witch of Agnesi, 29. A bifolium, 31. The folium of Descartes, as in René Descartes, 32. Parabolas and circles, hyperbolas, ellipses, cruciforms, asteroids, lemniscates, and kappa curves. All these famous curves have weird equations, and you can find slopes of tangent lines if you know how to differentiate implicitly. Have fun.